So that's another thing. I do these lectures. A lot of times I just say, we're canceling it today, but I do these and then the high school kids get to see them too. So that's fun. Because it's way better than the stuff I did last year during the pandemic. That was in a shed somewhere. I put a whiteboard up and I videoed for 5 minutes on my phone and then uploaded to YouTube and just kept doing that nonstop. Oh my God. Yeah, this is obviously not online classes in the sense of, one, there's someone in the room, but two, an online class would be properly set up to make use of being online. There'd be IT people managing how you do the classes, how you do the presentations. You know, there'd be infrastructure for doing it online. This is called emergency remote teaching. And we've been doing it for over a year. So, yeah. Anyway, where we left off, energy density in the wave. And we expressed it in terms of the electric and magnetic fields. And the bit we left out a little bit was that single serving of crayons. That's weird. So people looking, someone left up here 4 crayons in a package, like a pack of ketchup. Anyway, yeah, it's time to go outside and enjoy the weather, and we got to get through two more classes. All right, the energy is stored in a capacitor and is stored in the electric field, and so the energy of a capacitor, we usually express it as a function of the potential difference, but we can express it as a function of the electric field, since the electric field is uniform in a capacitor. And similarly for a coil will store energy in the current flowing through it, but it's ultimately expressible in terms of the magnetic field. And so, you know, energy looks like the field squared. And so we have an expression for the energy of a light beam in terms of the electric and magnetic fields in that light beam. And this is the sort of thing where it is reasonable to measure, you know, using a receiver, the strength of the electric or magnetic field, and use that to calculate the energy available. Oh, this is one where I make it advanced. So, you know, we talked about some examples. First off, we also talked about the RMS energy, which is the average energy density, which is, you know, you can't average a sine wave. Sine wave goes to 0, but you average the square of the sine wave. And what we do is we take, you know, if you try to take a proper average of the sine wave, you end up with this factor of the square root of 2. All right, so you just have to remember that that exists. And in vacuum, the electric and magnetic fields are related. In materials, this does not hold. If you have light passing through glass, the light will interact with the atoms in the glass, and the electric fields and the magnetic fields will interact differently. And so the waves will not have this nice relationship between them. But in vacuum, we can simplify everything. The energy density is only a function of the electric field or only a function of the magnetic field, whichever one we know. Of course, it's still a function of both of them. It's just that there's a nice relationship between them. So we worked through a problem of calculating the energy in an electromagnetic wave where we knew the electric field and we knew the maximum value. So we found the RMS value and then we calculated the energy. And we used that to also calculate the magnetic field based on the relationship between electric and magnetic fields. So what we really wanted to get to was intensity, because intensity is sort of more useful to us in a sense. Right? The intensity of a wave lets us, calculate the power it will deliver over time. And so we have a function for that. And the intensity looks like the energy density times the speed of light. Because you're think of a hunk of energy like a rock, and you're throwing it, say, through a window. How many rocks can you throw through the window? That's how much power goes through some area is your intensity. And then you're just throwing hunks of energy. And when you do that, there's some rate at which you can throw it, which is the speed of light. And so we work through a problem using that. What is the intensity of electromagnetic waves leaving the sun and coming to Earth? So at the position of the Earth. And the point of this is to talk about the energy available for solar cells. Right, that is that solar cells are going to absorb light. So you have some area to absorb, and you have the electric field at the top of the atmosphere in vacuum. So you have some intensity up there, which was 1,500 watts per square meter. But then you have some absorption as it goes through the atmosphere, and you have some efficiency in the solar panel, and you have it, you get cloudy days and nighttime. So, solar panels work a lot better in space than they do on Earth. Just a function of how the Earth works. So this is the new stuff. Now, everything we covered prior could be on the final, is on the homework. This stuff is brand new. This is not like we've seen it before, but we've seen it in different guises, and it's not on the homework, so I'm not going to put it on the final. This is Doppler. Yeah, we've seen Doppler effect in sound. So this part of the class is what I would call, how do you beat a traffic ticket or a speeding ticket, to be clear. Right? How does the cop measure your speed? Now, of course, they do other things, right? If you've seen the lines on the interstate, they paint lines across the lanes. That's the timing lines for aircraft. They just watch your car, and it travels a measured distance in a measured time to calculate average velocity. And it's usually something like half a mile or quarter mile in. And they have a particular time. If you're faster than that time, you're speeding, and they can calculate your speed. But what they do now is just paint the lines and put the signs up, and they never fly. Yeah. But they actually did fly for a while, until I realized how much they were paying per speeding ticket. They're basically losing money on the deal.
How did that work? Did they mail it to you, or would they radio to the cop?
They'd radio to a cop on the ground.
Okay.
They still do the same sort of thing with cops on bridges, but then they'll just radar gun you from the bridge and radio ahead to another car. So, yeah, that's the thing. People, I never understood high-speed chases. You can outrun one cop. You can't outrun the radio.
That's true.
So anyway, most of the time, if they're not doing something like cameras or aircraft or physically timing you by driving along and waving at you through the window, then they're using radar guns. Which what happens is they send a pulse of light out. It reflects off your car, and because your car is a moving source, there's a Doppler shift involved. The frequency they pick up coming back is shifted. But you can't use, I guess you could in principle use the formulas that you use for sound. There's no reason fundamentally why they wouldn't work. But it becomes unclear what we mean by the velocity, because when we talk about the velocity of stuff moving for sound, Doppler shifts, screens went off. I can keep talking because, so sound required a medium. And so the velocities were always relative to the medium. It was measuring your speed relative to the air. Right. And so that's why you had such complicated formulas. But when we talk about light, light doesn't require a tangible medium. It just has electric and magnetic fields. And those things are already present everywhere, and there's no real good way of measuring relative to the background electric and magnetic fields. Ultimately, what's going on is this goes into relativity, and we are going to cover a little bit of it the last class, just the highlights, not the math. But the gist of it is, all right, we talked very early, like in 111, very early in 111, about when we measure velocity, it's always relative to something, right? If you are driving a boat, you can measure the velocity of the boat relative to the water you're in, but you can also measure it relative to the land that the water is flowing through with some speed. And so you get addition of velocities, which is addition of vectors, and you get some weird stuff going on. So when we did sound Doppler, what we had were velocity vectors, and we had a preferred frame of reference, which is the air. All right, but relativity tells us that there is no preferred frame of reference. And we'll explain why that is in a little bit. But ultimately, for the purposes of light traveling between us, it doesn't matter if I'm moving at 60 miles an hour or if the cop is moving at 60 miles an hour. The relative speed between us comes out to the same number. And we will both measure the speed of light to be the same. Whereas in sound, we might measure different speeds of sound on top of the fact that we can deduce one of us is moving relative to the air and the other one isn't. All right. We can do this by measuring the Doppler shifts and determining, if one of us was moving, you'll get one Doppler shift, and if the other one was moving, you get a separate, different, distinct Doppler shift of a different value. Right? We don't do that with light. If there's any motion between the observer and the source, you get the same Doppler shift regardless of who's moving. So that's the thing is stated here. For sound, it's motion relative to the medium. For light, it is only motion between source and observer. There is no medium to care about because there's no preferred frame of reference. So that simplifies everything. We don't have to keep track of the speed of the source and the observer. And the speed of sound now becomes the speed of light. And so we get a simpler version, though you'll note one caveat that's here. Go back. One caveat that's here is, all right, because of all the relativity talk I was talking, if the speed between the things is large, close to the speed of light, and a ballpark figure is, say, 1/10 of the speed of light, as a rule of thumb, is if you're using 10 to the 8 meters per second, you need a different formula. 10 to the 6 is okay. That's 100 or less. 10 to the 7 is like you can calculate both ways and see if there's a difference. All right, the idea is that everything relativistic is just a correction. All right, because it has to be true for things moving very slow as well. All right, it just relativistic stuff means if you're going faster, you add a correction term. So anyway, the observed frequency is either going to shift up or down. If something's moving away from you, it shifts down, which means you take the minus sign. If it moves towards you, it's higher frequency, so you take the positive sign. So here's how the speed trap works. You have a cop side of the road with a radar gun, emitting some electromagnetic wave. In this case, it is 8 times 10 to the 9 hertz, which is 8 gigahertz, which is reasonable. So if you have a radar detector in your car, what's going to happen is, let's try to put this in colors matching this diagram. The wave travels out to you. So there is the frequency that the cop sends out. Then you and your radar gun are going to measure a shift, which I'll call S1, which is, and it is getting, because it's head on here, so it's going to be positive. Then that signal is reflected. And now, so the cop sees a wave coming back to him. And what he observes I've done that poorly. Give me a second here. Which is based on the signal that you heard times 1 plus V over C. And so you can relate these things, right? F observed is going to be F of the cop times 1 plus V over C times 1 plus V over C. And so you get some, this thing you can FOIL out, but this will be the observed frequency is the actual source times, this thing is 1 plus 2V over C plus V squared over C squared. But this is where we get into something what's called taking an approximation. Right. So we've done this before. If you remember when we did periodic motion, when we talked about a pendulum, there was what's called the small angle approximation, which is saying if your angle is small, you can assume that sine of the angle equals the angle itself in radians. Right? And that, when we did pendulums, we told you not to pull the pendulum back too far. And then we told you that there's periodic motion, the amplitude was roughly constant, without losses, and the period was a function of the length directly, and it was not a function of the amplitude. But that's not true, and the reason for that is you have circular motion, and your restoring force, or the restoring torque on a thing, is a function of sine of the angle of how far you pull it back. So if you pull it back a very small amount, sine of theta looks close to theta. But if you pull it back a lot, like pi over 2, then sine pi over 2 is about 1, which is not pi over 2, right? So there's error buildup when you pull it further and further back. And so to correct for that, you have to add more and more terms. But what we do is we take the approximation. If you just pull it back a little bit, then you're fine. So in a lot of cases, we can just neglect the small term. And when we look at this, all right, so our frequency is 10 to the plus 10 hertz, roughly. And then our speed of light is 10 to the 8 meters per second. But a car is only going to drive about 60 miles an hour, ballpark, which means about 100 kilometers an hour. So 100,000 meters per hour, which is getting several hundred meters per second. Not, our ballpark is nowhere, the speed of the car is nowhere near the speed of light. So the fraction V over C is small. And if V over C is small, then V squared over C squared is tiny. All right, V over C is going to be less than 1. And then V squared over C squared is going to be much less than 1. So we ignore it. So we can write F observed is approximately FS1 plus 2V over C. What all that means is if it reflects, you get a factor of 2. Now, you don't have to do that. You can calculate the long way around, but it's just explaining what's going on is you're doing 2 Doppler shifts. You're going to get a squared term. You can ignore the squared term because it's tiny.
If it bounced off a third thing, would you just change it to 2 or 3?
I think so. So completely off to the side, it would be 1 plus V over C cubed, because you'd get 2 reflections. So if you were trying to measure the reflection off the cop car, that would be the case this happens. If it's off of a third independent thing, you got to kind of figure out the relative velocities between them. But this would be like 1 plus 3V over C plus 3V squared over C squared plus V cubed over C cubed. And then V squared over C squared is tiny, we ignore it. And V cubed over C cubed is extremely tiny, we ignore it. And so you would approximate it as 1 plus 3V over C. All right, and I'm going to erase that because that is did it just cut off again? All right, why did it do that? The projection in the room is absolutely bull crap. It's just saying, no, we can't do that. So we'll shut it down and restart it. In the meantime, you see that?
Yeah, I can see that.
All right, we'll just keep going like that until it decides it's going to behave. Because the Zoom call don't care. All right. So the car observes in its radar detector, let's say, one Doppler shift, and then the police car observes another Doppler shift because it's seeing only the light reflected from the car, which is Doppler shifted. And so what's going on is we're trying to measure the difference between what the cop sees and what the cop send out, which is at 2100 hertz. But it is a function of these different, right? FO prime is FO, So what this middle line is doing is distributing FO and then taking the difference. And then ultimately, we're left with this bit. That is the difference in the signal sent out and the signal returned. And in using that to calculate the speed difference, right? And what you see is that if you calculate it for these numbers, you get that the car is going about 40 meters per second. And now I remember that 60 miles an hour is about 25 meters per second. So this car is going
Like 80.
up to 100, maybe 90 to 100. All right, because 120 miles an hour would be 50 meters a second. So 80% of 120. It would be 80, and then 85. Yeah, high speed. So a lot of the stuff that you're going to do here is just like you're going to do with sound Doppler waves, except for the little bit where you have no need to account for the motion of both objects. You just figure the relative speed between them. So we have another example. This is an astronomy example. All right, and we're not going to do all of them. We're going to pick one and do that. So hydrogen atoms emit light. You saw this in the lab, 4 different wavelengths, and we give you what those wavelengths are. And lo and behold, it works now. I'm not going to fix this till class is done. So right, we have 656, 486, 434, and 410. I'm going to do 410. And here, I mean, for astronomy, we're going to take that something moving at 1/10 the speed of light is still slow enough that our numbers work. You know, that's okay. You can calculate, if we ever get to a relativistic correction, you can calculate that. But it's, you know, this is a slow speed object relatively. So what we want to do is figure out the wavelengths that the astronomer sees. Now, this is the thing is, all right, we can convert the frequency to a wavelength. So in our formulas, F is C over lambda. Yeah, our speed is frequency times wavelength, so that's good. So we can write our formulas as C over lambda observed is C over lambda of the source. 1 away is minus V over C. And so for 410, we'll have C over lambda naught is C over 410 nanometers times, and then this is the thing is that when we do relativistic speeds, just do it as fractions of the speed of light. So this thing in parentheses is 1 minus 0.1. So it's just 0.9. And the other thing we see is that we have C on both sides and there's no addition to screw it up. So we just cancel it. And then everything's invertible. So the wavelength is 410 nanometers divided by 0.9. And 410 divided by 0.9, we pull out the calculator, is 455, yeah. When something is moving away from you in astronomy, it is red shifted. And that's what it means is the wavelength gets closer to the red end of the spectrum than the blue end. It is always a longer wavelength. So, and then you can go through and calculate the other numbers. They all have to be larger because it all has to be a shift away. So, you know, a lot of these, why are these screws backed out of this light fixture? That's weird. Don't poke it. Not mine, don't poke. You know, we just have a formula and then we combine it with another formula, which is true, and do some algebra. And there's no reason why we couldn't go through and calculate, say for 410, we could calculate the frequency of that. And it's going to be 10 to the 8 divided by 10 to the minus 9. It's going to be about 10 to the 17, 10 to the 18 hertz. We could do that and then calculate for everything and it would work. Nothing wrong with that. All right. So we talked about light having electric and magnetic field waves. They're sinusoidal changes in the electric and magnetic fields. So you can ask, which way is the electric field pointing? And for generic light, it is in any direction. All right. But there's no reason why you couldn't filter out for one direction or another. As you can imagine, sending a wave down a string. You can shake that string up and down or left and right. All right. So in principle, you just shake it in any direction. And if you shook it at some angled direction, right, say like this, I'll use a double-ended arrow for these, then this is essentially one part to one side and one part to another. It has vector components. So we can pick two directions. We'll pick up and down, left and right, vertical and horizontal. All right, so we take a string, we can put it through a picket fence, a slot, and that slot selects for different orientations. If the slot's vertical and the string is oscillating vertically, the wave passes through. The slot's horizontal and the wave's vertical. Or if the wave's horizontal and the slot's vertical, it gets stopped. Right? One wave lets it move like a free end, and the other wave lets it move like a fixed end, which is not moving. So we can do that with light, and we can do it with particular materials. So for polarized light, we've selected out the electric field to oscillate along a single direction. The magnetic field will be perpendicular to this in principle. So unpolarized light, the electric field is in all directions because it's not right. Students have this image in their mind of a single ray of light, and that is the light. But if you have a source of light, it can have an infinite number of waves, in a sense. Eventually you get down to counting photons, and so it's based on the energy in the light. But it can be a beam of light that has structure. It has a shape, it has an area that it passes through, and you can't imagine it as a ray of light. You can imagine it as lots of rays of light. And so any particular chunk of it could be in some direction. And you would add all those chunks up to get the overall effect, which is ultimately that it's oscillating in all different directions for unpolarized light. But you filter it out in one direction, it's polarized in one direction. So the actual filtering, you have different ways of doing that. One way is to have a material like a plastic, let's say, and it has long oriented molecules, where the electric field's likely to interact more in one direction than it is in the other. And so it gets absorbed in one direction and not absorbed in the other. All right, so you could do something like that. There are other versions. If you ever go fishing, like you're talking beautiful sunny day, calm lake, and you're on a boat. There's two things you want to do. You would like to see the fish, maybe, and you would like to avoid the glare of the light off the water surface. And when light reflects off that water surface, the part that gets to the fish is polarized in one direction, partially. And the part that's reflected is polarized in the other direction, partially. And the partial bits depend on the angle that it is incident on. So there is a particular angle where it can be 100% polarized. And at other angles, it'll be fractionally polarized. So you use polarized sunglasses, which allow the light that goes to the fish and not the light that comes off reflected off the surface. Right. And so you have different sources of polarized light. You can manufacture light in a polarized manner. That's what lasers do. Because lasers are sources of light, which is basically like Xeroxing one photon. So whatever its polarization is, all the other polarizations are the same. So it comes out coherent and all polarized in the same direction. And so this is the thing, we're talking about the intensity of the light as it interacts with a polarizer. So if we start with unpolarized light, right, and then we put in a polarized material that is selecting for the vertical polarization. Well, certainly none of the horizontally polarized light will get through, and all of the vertically polarized light will get through. But what about the stuff that's in the middle, right? All the diagonal. Those things, the diagonal orientations, are going to have a horizontal component and a vertical component, right? And so it's going to block part of it and pass part of it. That seems like a weird thing, but this is what we find is that light can be broken down into ultimately just two orientations, up and down, left and right, horizontal and vertical. And so the portion that gets blocked is based on that particular angle between the component and the thing that's doing the polarizing. So there's a whole bunch of light. It's randomly polarized in all different directions. Ultimately, what it ends up doing, you're taking an average over cosine squared, which comes out to a half. Until you end up half the light gets through. The cosine squared, I'll show you where it comes in a minute.
That kind of makes sense because
so the intensity is a function of the energy density, which is a function of the electric field squared. So your electric field is these arrows. And so this angle theta is where you get to cosine theta. It's selecting for, well, it's either theta or phi. All right, so selecting for one of them, and you end up with a cosine out of it. We'll see in the next slides how it's defined appropriately. So we're picking the cosine component out of the electric field. So the intensity goes as that cosine component squared, and taking the average over that as a half. And then here is how they're particularly defining the angles. So what we do is we take and make polarized light. Right. And so the electric field in between these things, the polarizer and what's called the analyzer, that is completely vertical, completely up and down. But then with the analyzer, what we're doing is we're making brand new directions, diagonal and perpendicularly diagonal. All right. Those are our two directions. And so there's an angle in here. And what we're doing is picking out the cosine component relative to that angle between the analyzer and the electric field. Right? You don't have to think about the angle necessarily. You just have to realize that you're going to find the angle between the electric field and the material, and then use cosine squared of it.
So it's just doing the same thing again for a different orientation?
Well, what's happening is we started with unpolarized light.
Yeah.
So when it goes through the polarizer the first time, it does it for all the different sources, which means we just get one half. But now if we take one polarization and we pass it through at an angle to another polarizer, we lose cosine squared of theta of it. Right. So what this is a relationship between the intensity put into a polarizing material and the intensity coming out. All right. I know this seems like a weird thing, but the point of this is, let me find, if you'll bear with me for a minute. All right, so one polarizer is in the background and it is selecting the light the camera sees from the environment. All right, so it selects for, say, up and down orientation. And then the second polarizer in the foreground is filtering based on the light coming from the first. And so, all right, you can see as the angle increases, it gets darker and darker. Right? Now, this is the thing. What happens if you put a third polarizer in the middle?
Does it again?
It doesn't make it any darker, right? Right. I mean, it couldn't necessarily get rid of light that didn't make it through, but it could pass light that wouldn't ordinarily get through in the first place. All right, so let's see if this is the one I want. Note that it is a little darker. So one is the materials are not perfect, right? Is that a real polarizer will still let a little horizontal through. And the second thing is that when we talk about horizontal and vertical, it has an assumption that the electric magnetic fields are in phase. If they're not in phase, you get what's called circular polarization, which is that they kind of chase each other around in a sense. The easiest way of thinking of it is that the polarizer shifts the electric magnetic field out of phase a little bit. And so what happens is some light that is at the moment going through vertically might not be vertical when it gets to the other polarizer. So it gets blocked as well. But in general, pretend these things are just horizontal and vertical, ignore circular stuff because generally that doesn't come up here. That comes up in like radio antennas, and you can get circularly polarizing materials for like when you need that sort of light. But this is almost certainly just light is not completely blocked. All right, so he's going to turn it. Oh, it gets blocked. So this is where we bring in the question of putting the third polarizer in between. All right, so well, that's my job.
Is it because it's reorienting to
Yeah.
be diagonal so that
Yes.
some of it will still come through the closest
Yeah.
one? Because
So
it's not
yeah,
all...
so the farthest one away selects for only vertical. And then the nearest one selects only horizontal. So the light coming through the second one is diagonal. Stop that. Go back to this slide. So when it goes to the first one, then it is up and down. But then it's trying to select the second polarizer is trying to select along a diagonal direction. So whatever gets through it will be a diagonal orientation, and the intensity will go as a cosine squared. Then it goes to the horizontal one, and it's going to select on the horizontal orientation. There'll be another angle involved, right? It'll be 90 minus the first angle, but cosine squared of theta times cosine squared of 90 minus theta is not zero. So some light must get through.
So light only can't pass through when it's directly perpendicular to
Yes.
being selected.
Yes. All right. So I wouldn't spend that much time on this. Right? It's not just the fishing example I gave. Is that it does get used in a fair number of places that you wouldn't expect it to be used in. We'll go look at this example. You can work out going backwards what the angle has to be by measuring the intensity before and after. And so if the ratio of the intensities is 1/10, then that cosine squared term has to be 1/10. And that's what's happening. So the first light that goes through is 1/2. And then that gives you a factor of 1/5 is cosine squared theta. And then that lets you calculate cosine of some number less than 1 is an angle less than 90, and that's what you get. Right. So the applications, sunglasses can be polarized. Not all of them. Some of them are just filters. They just dim the light. But some of them, like the fishing glasses, are polarized to cut out particular orientations that arise from glare, like light reflecting off of water. If you've been to a modern 3D movie, right? The original 3D movies were what's called anaglyphs, and that you had the red and the cyan glasses, red and blue, and you put them on, and there were two projectors. One was filtered for red, one was filtered for blue, and they were offset so you get the 3D effect. So for modern versions, right, the idea is that seeing that red and blue effect is a little disorienting. It's not good, not comfortable for you. So what they go with is polarized light, because if you see it, in principle, you don't have to have the images off, and you can have the light overlap. And if you see without the glasses, it's two-dimensional. You just see a two-dimensional unpolarized movie. But if you see it with 3D glasses, your eyes introduce the offset. And one will see one light source and the other will see the other light source. And you'll see the 3D effect. And this is where you have a choice. Some will do one eye is horizontal and one eye is vertical. But the others that I've seen will introduce circular polarization, and there'll be sort of a left circular and a right circular, which is the magnetic field ahead or behind the electric field? By some definition of behind or ahead. It's unimportant exactly. It's just they're different. One will be a gain in phase, one will be a loss in phase, and it looks like a left or a right circular. So it just the materials inside will be differently oriented in the glasses. Right. And then we talked about the 3 polarizer problem already. And then in nature, molecules themselves, when they reflect or transmit light, they can do so in a method that prefers one polarization over the other. All right, so if light is scattered off an object, a molecule reflects it in some angle, and the steeper the angle, the more polarized it can be in some senses. All right, and as it depends on the material, depends on the optical properties. We're getting into a lot of stuff that's unnecessary to go into. All right, but ultimately, it comes up in a few different places. So a couple of places it comes up: cell phone screens, laptop or desktop screens, TVs, things that have LED projection, LED lighting can tend to have hidden polarized light. One of the things I used to do for my students at high school, we had a projector, a proper projector on the wall. And I could stand in front of it with polarizers. And so the projector has like 3 light sources, a red, a green, and a blue, and it makes a color image. So I could stand there and pick out. And with one orientation, it ended up being red and blue. So you got a magenta or a purple color. And then I rotate it 90 degrees, and I get the green image. And I could show the 3 polarizers. If I have a magenta image and I orient it with a green image, it cancels out. You end up with a black spot. If I slip one in, and I'll get a gray spot because the lights are getting through. So it was fun. And there's like, oh, it's a projector, there's nothing fancy about it, but for some reason the light source in it was polarized. I don't know why. Anyway, that's like extra light stuff. Like everything on the homework is about like energy density and intensity, that sort of stuff. All right, I'm not going to put a polarization problem. Doppler is almost certainly not going to be anywhere because I haven't seen it in the homework. But that's where I want to stop today. The last lecture will be, let's see, topics we could cover is atomic spectra, how does the atom work, and relativity. And they're just going to be highlights because we're out of time. And of course, if you had questions about the final, but prep for the final is look through the past exams. They're not going to be significant. It has to be easier in the sense that you have 2 hours and we've covered stuff that you've been tested 6 hours on. So to keep the same number of questions have to be easier. Sorry, to hit all the topics, they have to be easier, or to cut the questions down. I'm going to do it whatever makes it easiest to grade. And
Make the whole thing multiple choice if you want. I won't be mad.
I have done it in the past and it doesn't work out.
Yeah,
because multiple choice doesn't give you chances for partial credit.
that's what Dr. Freed was telling me. I just feel a lot more confident because if I get an answer that's an option, I'm confident.
Well, I have done that. Is for the high school kids, what I've tried is, here are the multiple choice answers. That's 20% of the problem, and the other 80% is doing the work. So you still have to do the work, but you can save yourself by guessing on some of it, but not completely.
Makes sense.
But that didn't work out for them either, because a lot of them would just default to guessing because they didn't pay attention. They didn't read anything and they didn't try anything. So, they didn't try to ask any questions. So this is like, oh, it's multiple choice. And then they get like a 20 or an 18 on it. I was like, what? You didn't show any work. So anyway, yeah, I'm done here. So
I haven't looked at the homework yet, so I don't have any homework questions.
all right. I don't think it's that terrible. It is wave stuff, and it is energy density and intensity. And I don't think that's terrible, but it depends.
Yeah, I'll mess with it. If I can figure out the equations, I'll be all right.
Okay.
Well, see you Thursday.
See ya.